Hey everyone, this is our Boeing Overhead Crane Senior Project, and our project team consists of myself, Jason, Cole, and Christian. Just as a quick introduction, our project sponsor is Industrial Engineering Senior Lead Josh Seelhoff. He has been with Boeing for about 24 years now as a tooling IE and has been our mentor for this project the past few months. As for our problem identification, we're investigating the feasibility of integrating an improved crane operating system into Boeing's Everett facility. Our primary goals are to reduce safety issues and high costs associated with crane operators, as there are approximately 7 reported crane injuries annually and also a cost of about $60,000 annually as well. As it goes for our research, the main topics we looked at were backgrounds of crane cabs, performing economic analysis, types of renovations, any legal concerns, automated solutions, and ergonomics. So one of the most significant constraints that exists for this project is the upfront costs, especially because of the economic impacts of COVID-19. Another is the cultural changes, which could affect current workers' enthusiasm and willingness to apply their seasoned crane operating skills to an operation they aren't as familiar with. Other constraints include hardware compatibility and facility layout constraints. And operators' duties include using hand signals to guide the movement of the crane to carry large components and, of course, to participate in proactive safety improvement activities. Our project mentor, Josh, was able to provide us with reported injury data from 2015 to 2020. We created a breakdown of reported crane cab injuries, and we were able to determine that there were about 7 crane-related injuries per year. In addition, we conducted some literature research and saw that musculoskeletal disorders, lower back pain, and discomfort from the forward bent sitting position of overhead crane operators was also prevalent. This is a flowchart of the current state of how crane cab operators access the crane cab for their shift. They first ascend to the cab, then they operate a cab for about 2 hours, then they descend back down to the shop floor. We'll show in our AnyLogic model several potential areas for injuries. So we inputted the process flow into our AnyLogic simulation model. There are 2 separate types of paths for our model. They're the minor injury path and the major injury path, each with their different injury rates. Injuries are considered major if they require paramedics to be called on site. So walking through the simulation, they first start riding the elevator 70 plus feet in the air. Then they scale through the railings and walk through the catwalk to access the cab. Note there are several potential areas for injuries as we go through these slides. An operator must sit looking down through the legs for several hours a day to perform the job move. Then the latter half of this path just shows the descension of the cab operator down to the shop floor. The bottom circle path is actually the simulation for if a major injury will occur and paramedics would rescue the cab operator in an emergency situation. So after running the simulation 30 separate times, these were the results as a per year rate. There's an average of about 7 minor injuries per year and 1 major injury per year. The probabilities for injury rates were determined through injury report data provided by our project sponsor. And here's a 3D simulation just showing how the crane cab operator will be picking up large components to another part of the facility.
All right, so looking at our sample size of 30 simulation runs, we saw there were 21 instances in the system where at least 1 major injury occurred. And we were able to see that it could take up to about 24 minutes for paramedics to rescue a cab operator from the crane cab. And in order to figure out how well any implemented changes would be received by Boeing's crane operators, we conducted a survey asking them to share how many years they've worked as an operator, in addition to answering these 4 questions about their work environment. Interestingly, although only half said it wasn't ideal for working long hours, the majority did not notice any opportunities for improvement, which could indicate that they are willing to forego a certain level of comfort if it means being able to work in an environment they're already familiar with. We initially hypothesized that, let's see, next slide. Yeah, we initially hypothesized that there would be a correlation between an operator's level of experience and their reluctance to make changes to their work environment. However, the p-values from these correlation matrices that we made shows that there is in fact no correlation. So that concludes the background information and data that we use to formulate our potential solution alternatives. So our first alternative is having operators control the crane from a safe remote location off the factory floor. This, as far as from a feasibility and implementation standpoint, This would be the relatively most straightforward because radio frequency technology is already so widely used that companies such as Siemens and ABB have developed RF retrofits specifically for overhead factory cranes. The operator wouldn't be far from the floor and would still have a view of what's going on. And this would also open the door for workers with disabilities who would otherwise be unable to perform a job that requires them to be in an uncomfortable, difficult to access cab. On the other hand, there's a bit of a gray area as to who can and can't be a crane operator and what their responsibilities are. The factory would also need to be modified to accommodate remote control rooms. So this flowchart outlines the process by which an operator would perform their job from a remote workstation with outcomes that depend on safety issues that may be present or whether or not they still have any unfinished work. As you can see, it's a relatively simple process that doesn't require much movement. And this is the same flowchart and put it into AnyLogic, which simulates the operator entering, performing a move, and leaving the remote workstation. And after running our simulation 30 times across a period of 2 years, these graphs show the injury rate for a remote workstation per year. We determine an average of 2.2 minor and 0.35 major injuries per year for the remote workstation, down a significant 60% from the current state averages. This visual demonstrates how a crane movement would be performed from a remote workstation. In this example, the operator is in an elevated control room that gives them a bird's eye view of the factory floor. The control panel shown is made by cone cranes, so that that technology already exists, which would help make implementation obviously much more convenient. And through a network of cameras and sensors, the operator is able to move the crane and hoist the component into final assembly. And this is a rendering of what the control room would look like if Boeing decided to have multiple operators controlling multiple cranes simultaneously.
Awesome, thank you, Christian. As it goes for the second alternative solution, we take a similar approach to the first with removing the operator from the cab. This solution is called the factory floor solution, and the operator uses a belly box controller to transmit controls. Some of the pros of this solution include quicker changeover from shift to shift. The operator is no longer sitting uncomfortably, which is a huge ergonomic success, and there is already technology available. The cons of this solution, however, are the potential hazards of multitasking, that being walking and focusing on operating the crane cab at the same time. And then the unions would need to be involved with regards to the change in work requirements. The general workflow for the belly box solution is similar in simplicity to the remote workstation. An operator's day would begin by entering the shop floor. He then proceeds to the equipment room to obtain a belly box controller. Once the operator has the controller, they proceed to the crane, sync up to that crane, and begin performing crane moves. If the operator gets injured, then the crane operation must be halted. Otherwise, the operator completes his duties and continues this cycle. Our team created an AnyLogic model to test this workflow of the belly box solution for the injuries. The model starts with the operator going to get a belly box in which we immediately go to do an injury check. Then the operator proceeds to making his crane moves for his shift, followed by another safety check. Lastly, the operator discards the belly box and ends his shift. We simulated this previous AnyLogic model 30 times over a 2-year duration, and were able to generate a predicted average minor and major injury rate per year. As you can see, we believe there will be approximately 3.25 minor injuries per year compared to the current 7.3. We also believe there will be a 0.63 major injuries per year compared to the current 1.1. These injury rates are slightly higher than the remote workstation solution due to the potential hazards of being on the shop floor. However, they are 55 and 42% reductions in injuries, respectively. The implementation and functionality of the solution follows. Boeing first establishes an equipment room, then an operator would go to that room and secure his belly box controller for the day. Next, receivers would need to be integrated onto the crane for the controls. Then as the crane operator is making his crane moves by using the controls on his belly box, he is also walking alongside the crane as it moves. Once he gets to the drop location, the operator maintains a good view of the plane part and is able to communicate with his fellow hook tenders easily. Like I said before, this technology already exists in the airline industry, making proof of concept, implementation, and consultation with solution providers timely and efficient.
And then for our third and final solution, the ergonomic approach, we plan to redesign the ergonomics of the work environment to prevent fatigue and optimize performance. So some pros for this system are no significant changes to the roles or responsibilities for the operator, very inexpensive, it's a lot faster to implement, and there's not too much drastic change within the system. However, the operator still remains in the crane cab, and the crane cab related accidents still remain a concern, even though they are a little diminished. However, it could take longer to see these improvements. The implementation and functionality of this system is very similar to the current system with minor changes, such as the operator moves throughout their environment, scales the stairs, goes up to the second floor. But for instances such as scaling this rail, we would plan to implement a safety-proof door that would allow the operators to pass through without accidentally falling through or getting injured by. And then moving through the catwalk, there's not too much more interference here for operators to get injured. However, coming through and passing actually into the crane cab, the operator has to duck within this box here. So we plan to actually replace this with another safety-proof ladder to allow operators to pass through safely and easily, but also make sure that these areas are not easily able to be passed through under non-safety circumstances. And as the operator enters their workstation, there are these points of head strike that are of concern, and we would plan to pad these or make these more easily seeable by these operators, allowing them to avoid these circumstances. And as they go into their crane cab, this is an instance of a chair that offers full mobility for these operators, actually swiveling 360 and moving forward and backward for the operator to move through their environment. However, Boeing actually has grates for the walls and the floor for the operator to look through and talk through and communicate with their fellow peers, so they're not able to have a miscommunication or not see something, as in this floor that would be blocking them. And for the injury profile for the prior to improvement, we have ergonomic injuries, sprains, and the neck, the back, and the trunk all under inspection. So for this actual Boeing provided safety cost analysis, we have the severity levels of high, low, and moderate for these injuries, along with probabilities that are variable, such as the probable, likely, and probable probabilities in the beginning, and then the unlikely, probable, and unlikely following, going with less annual frequencies, leading from prior to improvement cost of around $61,000 to an after improvement cost to around $13,000. And for our decision matrix, we investigated operator safety effectiveness, which is the highest weight for this system, followed by productivity and capabilities, and ease of implementation, which are the second highest degree for this. And then we have cost of installation, cost of operation, and lifespan, being that the factory floor operation maximized productivity while improving the operator safety and prolonging the lifespan of the operation, being our final conclusion for this project. We operated through Cisco WebEx for our meetings with Josh Seelhoff, and we worked directly with Josh Seelhoff through these meetings. Our project schedule was dictated by these meetings with Josh, and we were able to conduct our personal research on top of that. And here's our works cited for our project, and we thank you.